All right, what I want to do next is put duration to good use and talk about how to approximate the change in prices when you have an interest rate change. Um, I suppose it's a little silly to do all this, just when you have computers to do this. I'm not really sure I get the point in all this, but it is a topic on exam FMs. Yeah, let's talk about it. Okay, so remember the linear approximation, not necessarily for just price, but for any function of any variable, really. Let's say the variable is I, is so if you start off with an interest rate I0, let's say, and you want to move to a new interest rate, the new price is roughly the old price plus derivative times the change in interest rates. And remember, the picture is as simple as follows. Um, here's a price function. Actually, it'll usually be decreasing, but whatever. For pictorial sake, yeah, this is my blue, the actual curve. The pink is the line, the tangent line, and the tangent line is approximately the actual curve. In other words, you know, for an interest rate change I, we roughly have the actual blue price is the pink approximation. Or in other words, again, the pink curve is close to the blue curve as long as we're at an interest rate near I. All right. And if you want to solve for the percentage change approximation, well, remember the percentage change is literally the new price minus the old price divided by the old price. So all you have to do here is just simply subtract off the so take this here, subtract off the old price and divide by the old price, and we get the following. And this is nice because remember, modified duration is minus p prime over p, so minus minus cancels. So we have this nice easy peasy formula that percentage change is roughly modified duration times change in interest times 100%. And we're taking modified duration always with the original price. So that gives us the conclusion of the percentage price change is roughly the modified duration times change in I. And we will kind of show in a minute how you get modified duration into this. It's actually pretty obvious what you would do. Where you have P prime times change in I, you would just multiply and divide by the original price. Right. Do that in a minute. All right, so easy example. This is 152 in the sample questions. So let's pop that up. Yeah, there's no rhyme or reason to the numbering here. Just be aware of that. So you have a 20-year bond, yield of 10%. I'll call it duration of 11. Yield increases by 0.25%. So we're adding that 0.25% to the 10% for a total of 10.25%. Or in other words, the change in yield rate slash interest rate, same thing, is 0.25%. So 0.0025 as a decimal. And when we're using our approximation formula, you do want to use interest as a decimal. Find the bond's approximate percentage change. So pretty straightforward. Give me a second to new here. Okay, and just be aware that we're not taking 10 and increasing it by 0.25%. We are just adding 0.25% to 10%. I actually used to think I was doing the former, and I was all confused. And actually, someone on some random person on the YouTube video that I had in the past was like, "No, no, no, it's you know you're doing this wrong. It's just an incorrect interpretation. So just be aware of that." Okay, so one, two. So first thing is first is that we're not given modified duration. We're given Macaulay duration. That's fine. 11 is MACD, and that is 1 plus I, which is 1.1, because I is 10%, or rather one, it's so, sorry, I want modified duration for my original interest rate. My original interest rate is 10%. So here it's 1 plus my interest rate as a decimal times modified duration. Uh, MOD, but MD. All right, so fairly trivially, MD is 10. And so what does that mean? Well, also, as I mentioned, you don't have to do anything for a change in interest. It's 0.25%. So that's 0.0025 as a decimal. All right, so that means the approximate percentage change is going to be minus 10, which is modified duration, times 0.0025 times 100%. Pretty easy problems. M times this one, minus whatever. All right, so minus 2.5%. So these are always going to be negative when you have interest rate increases. Remember, basically everything we have and will do, prices decrease as interest increases. So price of the bond decreases by 2.5% roughly if we go from a yield of 10% to 10.25%. And that's right. The one thing to be clear, I don't care if this is a bond, an annuity, or whatever the hell it is. That's completely irrelevant. They're just giving you all the information you need to do first order modified approximation. And also, why is it called first order modified? First order, what does that mean, first order? It's really dumb. But first order means you're doing the linear approximations, the first order in Taylor series. Taylor series approximation. I say it's dumb because there is no second, third, fourth, whatever order on exam FM. So why not just call it modified approximation? I have no idea. All right, so yeah, let's do what I mentioned you could do before. Let's get modified duration in the mix here. So do it what I mentioned. You just take this, minus minus makes it a plus, and multiply and divide by the original price. And the whole purpose, of course, is that this is modified duration. And this is nice because I have the original price here, original price here. And so I can just factor it out. And we have this nice, easy peasy formula that we have an interest rate change from I0 to I. Then roughly the new price is the old price times 1 minus modified duration times the change in interest rate. Where for change in interest rate, we're dealing with death. So like I said, these problems, there's no rhyme or reason for the numbers. So go back roughly 100 problems and we have almost the same problem. Wild, but uh so one All right, so Krishna buys an N-year 1,000 bond at par. The Macaulay duration is 7.959, interest rate 7.2. Calculate the price of the bond using first order modified approximation if the interest rate rises to 8%. Okay. So the bond is bought at par, so yield is the coupon rate. So otherwise it'd be confusing. Do they mean coupon? Do they mean yield rate? Not. I don't care if it's N year. And sometimes I don't care if it's bought at par. I guess you do care because that means that otherwise you don't even know if the price is 1,000, but you do know the price is 1,000 now. But if I was just given the price of 1,000, then that's enough to do everything. So this is a really easy problem. So just like before, I need to get the modified duration, and we do that just like before. 7.959 is MACD. The interest rate here, the original one is 7.2%, so 1 plus that is a decimal, times modified duration is Macaulay duration, so just simply divide, store it. 7.959 over 1.07. Go ahead in one spot. Okay, now plug and chug. So the approximate price is the original price 1,000 times 1 minus modified duration. Write that. $7.42. Uh, 7. So be careful. Do use percentage decimals. So it's 0.08 minus 0.072, 0.008. Don't want to input 0.8. You'll get a very, very wild answer. See that? There's not a gigantic interest rate change, so it shouldn't change that much. I'll put some calculator. 0.008 minus 0.072 times 1. Negative plus 1 times 1,000, and we get the answer 940.60. Which is right here. Okay. All right, so let me talk about something that is bizarre. Again, I don't really see the point in this, but all right. So this is actually, you can prove, is a better approximation than modified approximation. And I have a video on where this comes from. It's actually quite interesting. Um, what you do is linear, you take this function here, so do the linear approximation with respect to price times 1 plus I. This to the MACD. Yeah, so you look at this function here, and you basically use the chain rule, taking derivative, but the linear approximation, and you basically solve for P of I in your linear approximation. That gives you, believe it or not, this is roughly 0, 1 plus I 0 over 1 plus I max D of I. Yeah, I would go look at the video if you're interested. Pretty straightforward. Um, Video. Yeah, here we go. Derivation. First order Macaulay approximation. Yeah, if you're curious kind of where on earth this comes from, go take a look at this video. Basically do what I just mentioned a second ago, and in particular, right, I basically, yeah, I define this function g, do first order approximation on g, and solve for um, uh, approximate price change. Or sorry, solve for the approximate price P of I. Yeah, and do exactly what I did before, solve for the percentage price change. You're gonna get that's roughly this thing right here. For exam purposes, it's just plug and chug. It's pointless, in my opinion, because it doesn't test that you know anything about finance, deriving it, or anything. I totally do not understand this topic in exam FM, but it's an easy topic, so. All right, so very similar problem to number 51. This is 153. Yeah, in that video, I show you the link where it's proved that Macaulay duration is always better than modified duration. It's actually pretty not serious math, but it's actually a interesting proof. Calculus on steroids. Okay. You have a bond. Price 1,000, just like before. Macaulay duration is 7.959. Everything's the same thing as before, except you're using first order Macaulay approximation, not first order modified approximation. So really, it's just plug and chug. I'll quickly remind you again. Well, actually, sorry. we needed modified duration before. Here we're given Macaulay duration, so this is really just plug and chug. Um, and if you put equals on homework or exams, it's fine. So it's 1 plus the original interest rate over 1 plus the new interest rate. Um, price. Sorry, it's 1,000 times this. Okay, yeah, 1,000 times this to the 1 over MACD. Sorry, to the MACD, not 1 over. So MACD is 7.959. Five. Fix that one. Just plop this in a calculator and see what you get. 1.072 over 1.08. Raise that to 7.959 times 1,000. 1 times 100, sorry, times another times 1,000, 942.50. So very close to the other one of 940 something, but this is a better approximation. 942.54 at least. So they do have 940.60, which is kind of mean because that's the modified approximation, but this is another almost the same kind of problem. 154, I'm not gonna do it. Yeah. Okay, one more example and we will move on to something a little different. Um, Same kind of problem, 146. That. Doing this. Fine. All I want to do is move this thing. Anyway, right. So, yeah, same as before. Go through this quickly, but using Macaulay approximation. First order Macaulay approximation. So, you can do higher orders of Taylor's theorem to the function I mentioned. That would get real ugly real quickly. And I'm not sure if anyone's ever even done it. I'm not sure there's a point, but you can, and that's why it's called first order Macaulay approximation. Again, it's stupid because if you're going to specifically call it first order, you should have second order, third order. There isn't for examinations. Right. So, yeah, I don't care if it's a bond, 20 years, irrelevant. So the answer is just simply one plus the original interest rate over 1 plus your new interest rate. So if we start off with 10% and we increase it by 0.25%, 10.25. Again, I'm not saying we take 10 and increase it by 0.25%. I'm just literally saying, and what this problem is saying is you take 10 and add 0.25 to it. Yeah, it's a little confusing. I think it's confusing, but this is what they mean. So get used to it and deal with it. Yeah, I always felt exam FM is way more confusing than exam P. P I always thought was extremely straightforward, maybe a little difficult, but definitely straightforward. So yeah, one plus my original interest rate over one plus my new interest rate to the MACD minus 11, sorry, minus 1 times 100% to get 1.1 over 1.1025 11. Um, yeah, so it's yeah, some reason my brain had a part there. Um, okay, so that gives me, we plot this into the calculator, 2.47 percent minus. It's definitely minus because we have an interest rate increase, and we know everything we do decreases as interest increases. So it's going to this new yield rate of 10.25% from 10% corresponds to roughly 2.47% drop in the bond price. And that is right here. Let's say I have two annuities that I want to buy. Let's say P is the price of these two annuities. And let's say P1 is the price of the first annuity, P2 is the price of the second annuity, all at some interest rate I. Okay. So I claim, and I'll show this very quickly because it's very easy to do. It's not magical or anything. I claim that the Macaulay duration corresponding to this interest rate I is given by the following formula. You just multiply first price times the first Macaulay duration. This is Macaulay duration corresponding to the first annuity that we're purchasing, PI, with price PI rather. So it's P1, first price of the first annuity times the Macaulay duration for the first annuity, plus the price of the second annuity times Macaulay duration corresponding to the second annuity over the total price, P1 plus P2. So how do I get that, and where on earth does this come from? Well, let's say, yeah, so P, remember, is P1 plus P2 of I. Okay. So I need, let's get so let's get MACD corresponding to the sum of these two annuity prices. This is just, well, by definition, 1 plus I times modified duration. So it's P prime over P. All right, so I just got to get what P prime is. I know what P is. It's just P1 plus P2. So I know what P prime is. It's P1 prime. And I'm distributing the minus 1 plus I. So it's P1 prime minus 1 plus I, P2 prime over P1 plus P2. Okay. Well, let's just relate these two quantities to the Macaulay duration of P1 and P2. So Macaulay duration P1. This is just, again, 1 plus I times modified duration for P1. So, so minus So it's P1 prime or P1. All right, so lo and behold, how do we get this quantity here? I just multiply. Okay, so P1 price times the price of the first annuity at I times Macaulay duration of the first annuity at I is exactly what I want, minus 1 plus I P1 prime at I. Okay. Okay. So this here is really P1 and nothing different with this. This is this whole thing here is also it's the same thing, except with respect to well, P2 instead of P1. It's P2 of I. That's a little messy here. You do exactly what I did, but instead do it for P2 instead of P1. So it's P2 I times Macaulay duration, Macaulay, excuse me, kind of late here, at I. Okay, that's how we get our formula. This is exactly what I have here. So maybe yeah, I can't fit it here, but yeah, just kind of neatening up what I have. Just literally write this. Well, just yeah, this is going to be equal to P1 of I. Macaulay duration for first annuity I plus P2 over P1. Yeah, this is getting a little long, so I want to do an example and then probably just do the derivation of first order Macaulay approximation on a separate video. It's neat stuff, if particularly if you're an actuary, then I think you should kind of be interested in some of the math things. You are math majors technically, so all right, anyway. So that's how to get this very, very, very useful formula. Okay, so a really nice problem. One of the only nice problems I've seen for these duration type problems. So SOA life insurance company. Wow. Is that really? Yeah, like didn't even fix that typo. Okay. Well, not my problem. It's their problem. So, I mean, not this is just SOA Society of Actuaries sample exam FM problems as usual. So anyway, this has a portfolio of 2 bonds. Absolutely irrelevant that these are bonds. Bond 1 has duration 7.28, price 35,000. Bond 2 has Macaulay duration 12.74, 65,000. The price and duration calculated using yield rate of 4.32%. So when they say interest rate, they do mean yield rate. Bond coupon rates or bond rates are really irrelevant here. We don't need that. We just need an interest rate. Yeah, so the estimated price at an interest rate I using first order Macaulay approximation is 105,000, 105,000. using this approximation, determine I. Okay, this is actually a pretty easy problem. We just need to get the Macaulay duration for this portfolio and then plug it into the first order Macaulay approximation. All right, so let me first just plug and chug into this formula. So everything is going to be at this interest rate, 4.32%. I'm not going to rewrite all these I's. Okay, so let me, yeah, so 1 second. Okay, so MACD is sorry, P1. I'll go back in a second. P1 MACD1 plus P2 MACD2 over P1 plus P2. Okay, so go back real quick. P1 is 35,000, P2 is 65,000, 7.28 is the first Macaulay duration. The second Macaulay duration is 12.74. Plug all that in. So 30, I have this written down here. Where did it go? Right here. So 35,000. First price, again, first Macaulay duration is 7.28. 65,000 is the second price. Second Macaulay duration. Okay. Over the addition of the two prices, 35,000 plus 65,000. Okay. Well, you do this, I'll do this real quick in the calculator. All right, so 35,000 times 7.28 plus 65,000 times 12.74 all over 35,000 plus 65,000. Now this is my answer. I'll store it in one spot. $10.824. Nice looking number. And yeah, to be clear, this is, I'm going to use this in a second. MACD at my interest rate of 4.32%. So 0.0432. That's the interest rate we were given in this problem. Yeah. All right, so let me go back real quick. All right, so we're going to use this approximation here. The thing is, we're given what the approximate new price is. It's 105,000. Okay. We're given the total price. So we're looking at the value of this portfolio. So we really are using P in this approximation, Macaulay approximation, which is the addition of these two bonds. So the new price of these two bonds is 105,000. The old one is, well, the price of these bonds at this interest rate is just 35,000 plus 65,000, 100,000. We have my old interest rate, 4.32%. We have the Macaulay duration at this interest rate for this portfolio of two bonds. So we can all plug that in and then solve for I. So let me do all that. 1 second. So again, just a reminder of what we're doing. I'm going to say P is P1 plus P2. Price of these two bonds. So I'm going to rewrite the Macaulay approximation formula. One plus I 0 over 1 plus I to the Mac D of I 0. All right. So at my at 4.32%, the price of both of these bonds together is 100,000, as I mentioned before. 35,000 plus 65,000. We're given that the new price corresponding to the unknown interest rate is 105,000. My old interest rate is 4.32%, so this is 1.0432 in the numerator. We do not know what's in the denominator, so we're trying to figure out. But we just figured out the Macaulay duration of the sum of these two bonds at this yield rate, 4.32%, just because everything was priced at this yield rate. So, just to be clear, this did not come into the calculations here, just because we're given the price and Macaulay duration for both of these bonds at this yield rate. There's no need to do any specific bond calculations involving Macaulay duration. Okay. So, we calculate this to be 10.824%. All right, so I'm going to take, let's see, what's 105? 105,000 over 100,000. 1.05. Okay. So this is going to be 1.0432 over 1 plus I 10.824. So let me take 1.05, raise it to the 1 over 10.824, and that'll give me this fraction here. Okay, so let me go. Actually, I could just do this real quick. 1.05 to the 1 over 10.824. It's going to be 1.0432 over 1 plus I. So I'm going to get this and then just do 1 over and then multiply by 1.0432, and that'll give me 1 plus I. Okay, so let me go to the calculator. Okay, so I have 1.05 raised to the 1 over 10.824, not 1, 4. 1 over times 1.0432 to get, well, subtract 1 to get I and make it a percentage. 3.85%, and what problem is 190? I think that's there. Yeah, it's C. 3.85%. Okay, so not a particularly hard problem. You just really kind of you have to know what you're doing. And again, you know, with these problems, um, you're given Macaulay duration. You're given the Macaulay durations for both of these. You do not need to do any specific bond calculations here. You're already given Macaulay duration, so it is totally irrelevant that these are bonds. These could be any annuities whatsoever. So just be aware of that. If you're given Macaulay duration, you don't need to do specific bond calculations to get Macaulay duration or modified duration. Okay? You just need to know the formula for the Macaulay duration of a portfolio. And so it should be clear real quick. I don't think there's any problems on Exam FM on this, but so this formula applies to any number of pieces of a portfolio. In other words, if I have P, price of the sum of any number of annuities, the formula would be just P1, the Macaulay duration of the first annuity, the price of the first annuity times the Macaulay duration of the first annuity, plus the price of the second annuity times the Macaulay duration of the second annuity, plus the price of the third annuity times the Macaulay duration of the third annuity. Repeat that pattern all the way. The price of the last annuity times the last Macaulay duration, all over the sum of the prices. Exact same logic as before. To get the derivative of each of these kind of pieces of the annuity, you just use the fact that the annuity, the derivative, minus 1 plus I times the derivative would be the price times the Macaulay duration. So basically just do the same logic that we did before to get any number of the Macaulay duration for any number of the sum of any number of annuities. You really should be able to do that yourself if you're kind of interested. But okay, yeah, and like I said, and doing a separate video. This is definitely longer than I was hoping. In a separate video, I will derive the Macaulay approximation formula. All right, well, yeah, probably only 2 more videos, maybe even 1 more video. I don't know if even convexity deserves its own video. It's really just useful insofar as use it for immunization. But yeah, I'll definitely talk about immunization very soon. Very useful, practically useful, important topic. Well, so yeah, hopefully you didn't eat too much yesterday. I sure as hell did. Kind of suffered a little bit today, but probably tomorrow I'll have everything digested and out of my system and be back to new. All right, so long. Take care. Bye-bye.